Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. Why distant galaxies? Look red. When astronomers point their most powerful telescopes toward the deepest reaches of space, photographing galaxies billions of light years away, they notice something remarkable. These distant galaxies appear distinctly redder than nearby ones. Light that was emitted as ultraviolet or blue has been shifted toward red and infrared wavelengths by the time it reaches Earth. This redshift is one of the most important observations in all of astronomy, providing direct evidence for the expansion of the universe and allowing astronomers to measure cosmic distances and trace the history of the cosmos back nearly to the Big Bang itself. The primary cause of this reddening is cosmological redshift, a consequence of the universe's expansion. This phenomenon was first observationally established by Edwin Hubble in 1929, though the theoretical groundwork had been laid by several physicists, including Alexander Friedmann and Georges Lemaitre, who independently developed solutions to Einstein's equations of general relativity that predicted an expanding universe. Hubble observed that distant galaxies showed spectral lines, the characteristic fingerprints of elements absorbing or emitting light at specific wavelengths, shifted toward longer, redder wavelengths. Moreover, he found that more distant galaxies showed larger redshifts, establishing what became known as Hubble's law. The recession velocity of a galaxy is proportional to its distance. The expansion of the universe is not like objects moving through space. It's space itself that's expanding. Imagine the universe as the surface of a balloon with galaxies painted on it. As you inflate the balloon, the surface stretches and the distance between any 2 points on the surface increases. The galaxies themselves don't move through the rubber. The rubber itself expands, carrying the galaxies apart. This is fundamentally different from regular motion through space, and it's this expansion of space that creates cosmological redshift. When a galaxy emits light, that light begins its journey through space toward Earth. The light consists of electromagnetic waves, oscillating electric and magnetic fields propagating through space. As the light travels, the space through which it's traveling is expanding. This expansion stretches the wavelength of the light. Imagine a wave painted on a rubber band. If you stretch the rubber band, the wave gets stretched too, its wavelength increasing. The same thing happens to light traveling through expanding space. Light that began as ultraviolet with a wavelength of 300 nanometers might arrive at Earth as visible red light with a wavelength of 600 nanometers if it has traveled through enough expanding space. The amount of redshift depends on how much the universe has expanded during the light's journey. Astronomers quantify this using the redshift parameter, represented by the letter Z. A redshift of Z equals 1 means the universe has doubled in size since the light was emitted. Wavelengths have stretched by a factor of 2. A redshift of Z equals 2 means the universe has tripled in size. Wavelengths have stretched by a factor of 3. The highest redshift galaxies yet observed have redshifts around Z equals 13 to 14. Meaning the universe has expanded by a factor of about 14 or 15 since those galaxies emitted the light we now detect. These galaxies existed when the universe was only a few 100 million years old, less than 3% of its current age. For nearby galaxies, the redshift is small, perhaps Z equals 0.01 or less. The Andromeda galaxy, our nearest large galactic neighbour, actually shows a blue shift rather than a redshift, because it's moving toward us through space faster than the cosmic expansion is carrying it away. But for galaxies more than a few 100 million light-years distant, Cosmological redshift dominates, and the farther the galaxy, the larger the redshift. This relationship between distance and redshift allows astronomers to use redshift as a distance indicator. By measuring the redshift of spectral lines in a galaxy's light, they can calculate how far away it is and how long ago the light was emitted. A galaxy at z equals 1 is seen as it was about 8 billion years ago, when the universe was roughly half its current age. A galaxy at z equals 6 is seen as it was less than 1 billion years after the Big Bang, when the universe was still in its infancy and the first generations of stars were forming. Redshift affects all wavelengths equally, in terms of the stretching factor. Ultraviolet light gets stretched into visible light. Visible light gets stretched into infrared. Infrared gets stretched into far infrared, and eventually into microwaves. For the most distant galaxies, light that was emitted in the ultraviolet, the signature of hot, young stars, arrives at Earth as infrared radiation. This is why infrared telescopes, like the James Webb Space Telescope, are so valuable for studying the early universe. They can detect the stretched light from the most distant galaxies, galaxies so far away that their visible light has been redshifted entirely out of the visible spectrum. There's another related effect that makes distant galaxies appear redder beyond just the stretching of wavelengths. As light loses energy through redshift, longer wavelengths mean lower energy. The apparent brightness of the galaxy dims. A galaxy at high redshift appears fainter than it would if there were no cosmic expansion. Additionally, the rate at which photons arrive is reduced. If a galaxy emits 1 photon per second toward Earth, but the universe doubles in size during the light's journey, those photons arrive spread out over 2 seconds because the space between them has been stretched. This reduces the detected brightness even further. The cosmic microwave background radiation provides the most extreme example of cosmological redshift. This radiation was emitted when the universe was 380,000 years old, at a temperature of about 3,000 Kelvin. At that temperature, matter emitted primarily visible and infrared radiation. The redshift since that time is about c equals 1,100, meaning the universe has expanded by a factor of 1,100. Wavelengths have been stretched by the same factor, so light that was visible orange or red has been stretched into microwave radiation. The temperature corresponding to this radiation has dropped by the same factor, from 3,000 Kelvin down to 2.7 Kelvin today. It's important to distinguish cosmological redshift from Doppler shift, though they're related and can sometimes be confused. Doppler shift occurs when a light source moves through space toward or away from an observer. An approaching object's light is blue shifted, compressed to shorter wavelengths, while a receding object's light is redshifted. This is the effect that changes the pitch of a siren as an ambulance approaches and then passes you. For galaxies with relatively small redshifts, say Z less than 0.1, cosmological redshift and Doppler shift give nearly identical results and can be treated interchangeably for many purposes. But for high redshifts, the distinction matters. Cosmological redshift is fundamentally about the expansion of space itself, while Doppler shift is about motion through space. Redshift also allows astronomers to study the history of cosmic expansion. By measuring redshifts of many galaxies at various distances and determining their distances through other methods, like standard candles, objects of known intrinsic brightness, astronomers can trace how the expansion rate has changed over cosmic history. These studies revealed one of the most surprising discoveries in modern cosmology. The expansion of the universe is accelerating. Saul Perlmutter, Brian Schmidt, and Adam Rees shared the 2011 Nobel Prize in Physics for this discovery, made by studying distant supernova and measuring how their redshifts and distances deviated from what would be expected in a universe with constant or decelerating expansion. The acceleration implies the existence of dark energy, a mysterious component that makes up about 68% of the universe's total energy density and exerts a kind of repulsive effect that pushes space apart. This dark energy's influence has grown over cosmic time as the universe expanded and matter became more dilute. In the early universe, matter dominated and the expansion was slowing down. But a few billion years ago, dark energy became dominant and the expansion began accelerating. Distant galaxies' redshifts encode this history, showing patterns that reveal when the transition from deceleration to acceleration occurred. Redshift measurements also reveal structure in the universe. When astronomers measure redshifts for thousands or millions of galaxies, they can create three-dimensional maps showing how galaxies are distributed in space. These maps reveal the cosmic web, the filaments, walls, and voids that constitute the large-scale structure of the universe. Regions where galaxies are closely spaced show similar redshifts because they are at similar distances. Voids show up as redshift ranges where few galaxies appear. The chemical evolution of the universe is written in redshift as well. Spectroscopy of distant galaxies reveals what elements were present when that light was emitted billions of years ago. By comparing galaxies at different redshifts, different cosmic times, astronomers can trace how the abundance of heavy elements has increased over cosmic history as successive generations of stars created these elements through nuclear fusion and dispersed them through supernova explosions. Galaxies at Z equals 6 or 7 show much lower abundances of elements heavier than helium compared to nearby galaxies, confirming that the early universe was primarily hydrogen and helium, with heavy elements accumulating over billions of years. Even the shapes and types of galaxies change with redshift. High redshift galaxies tend to be smaller, more irregular, and more actively forming stars than low redshift galaxies. This reveals that galaxies evolve over time, growing through mergers and gradually building up their stellar populations. The universe at Z equals 2, when it was about 3 billion years old, was a much more turbulent place, with higher rates of galaxy interactions and star formation than the relatively sedate local universe we see today. Gravitational lensing affects redshift measurements in subtle ways. When light from a distant galaxy passes near a massive object, like a galaxy cluster, the gravity bends the light's path and can magnify the image. But it also affects the light's frequency. Different images of a gravitationally lensed galaxy, formed by light taking different paths around the lensing mass, can show slightly different redshifts due to the gravitational time dilation in the lens's gravitational field. These tiny differences help astronomers probe the distribution of mass in the lensing object. The reddening of distant galaxies is therefore not just an interesting observational fact, but a fundamental window into cosmic history. Every measurement of a galaxy's redshift tells us how far away it is, how long ago its light was emitted, and what the universe was like at that cosmic epoch. The systematic increase in redshift with distance directly demonstrates that the universe is expanding, that it had a beginning in the Big Bang, and that it's evolving over time. The precise pattern of redshifts reveals the expansion history, constrains the properties of dark energy, and allows us to trace the formation and evolution of structure across billions of years of cosmic time, making the reddening of distant galaxies one of the most information-rich phenomena in observational astronomy. What's left after a star explodes? When a massive star reaches the end of its life and explodes in a supernova, the detonation is one of the most violent events in the universe, releasing in a few seconds as much energy as the sun will radiate over its entire 10 billion year lifetime. The outer layers of the star are blasted into space at thousands of kilometers per second, creating an expanding shell of hot gas enriched with newly forged elements. But the explosion doesn't simply obliterate the star. At the center of the expanding debris, something remains, a compact, incredibly dense object created from the collapsed core. What gets left behind depends on the mass of that core and determines whether the remnant becomes a neutron star, a pulsar, a magnetar, a black hole, or in rare cases, nothing at all. The immediate aftermath of a core collapse supernova leaves behind a proto-neutron star, an extremely hot, dense ball of neutrons about 20 to 30 kilometers in diameter, containing between 1.4 and about 3 solar masses compressed into a volume smaller than a city. The temperature at birth exceeds 100 billion degrees Celsius, making it one of the hottest objects in the universe. Over the next 10 to 20 seconds, the proto-neutron star cools by emitting enormous numbers of neutrinos, ghostly particles that barely interact with matter but carry away 99% of the supernova's energy. As the proto-neutron star cools and stabilizes over minutes to days, it becomes a neutron star, a stellar remnant held up against further collapse by neutron degeneracy pressure, the quantum mechanical resistance of neutrons being compressed too closely together. The density is extraordinary, about 500 million tons per cubic centimetre, comparable to compressing all of humanity into a volume the size of a sugar cube. A neutron star is essentially a single gigantic atomic nucleus, held together by gravity rather than the strong nuclear force. The structure of a neutron star is layered and complex. At the surface lies a thin atmosphere, only centimeters thick, composed of hydrogen, helium, or heavier elements, depending on the star's history. Below this lies the outer crust, about a kilometer thick, where matter exists as a crystalline lattice of atomic nuclei, extremely neutron-rich nuclei unlike any found on Earth, embedded in a sea of electrons. These nuclei become increasingly neutron-rich with depth, containing far more neutrons than protons. Deeper still, at the interface between outer and inner crust, neutrons begin to drip out of nuclei, creating a neutron superfluid that coexists with the nuclear lattice. A superfluid is a state of matter with zero viscosity. It flows without any resistance whatsoever, a quantum mechanical phenomenon that can only occur at extremely low temperatures or extremely high densities. In neutron stars, despite the enormous temperatures by human standards, the density is so extreme that superfluidity occurs. The inner crust, extending to about 10 kilometers depth, consists of increasingly exotic arrangements of nuclei and superfluid neutrons. Computer simulations predict that nuclei might arrange into cylindrical rods, flat plates, or even more complex three-dimensional structures, nicknamed nuclear pasta, because of their resemblance to spaghetti, lasagna, and other pasta shapes. This nuclear pasta might be the strongest material in the universe, billions of times stronger than steel. Below the crust lies the outer core, where nuclei dissolve entirely into a uniform liquid of neutrons, with a small admixture of protons and electrons to maintain electrical neutrality. Both the neutrons and protons exist in superfluid and superconducting states respectively. The protons form a superconductor, where electrical currents can flow without resistance. This region makes up the bulk of the neutron star's mass and extends to perhaps 10 to 12 kilometers from the center. At the very center, in the inner core, where densities exceed that of atomic nuclei by factors of 2 to 10, matter might exist in states never observed in laboratories. Neutrons themselves might break down into their constituent quarks, creating quark matter or strange quark matter. Other exotic particles predicted by quantum chromodynamics, the theory describing the strong nuclear force, might appear, including hyperons, kaons, or pion condensates. The exact nature of matter at these densities remains one of the great unsolved problems in physics, accessible only through observations of neutron stars and theoretical calculations. Many neutron stars are born rotating rapidly, spinning tens or hundreds of times per second, inheriting and concentrating the angular momentum of the massive star's core as it collapsed. If the neutron star's magnetic field is tilted relative to its rotation axis, which is common, the neutron star becomes a pulsar. The magnetic field, enormously compressed and amplified during the collapse, can reach strengths of 1 trillion times. Earth's magnetic field. Charged particles accelerated along magnetic field lines near the poles emit beams of radiation that sweep through space like a cosmic lighthouse. When one of these beams sweeps across Earth, we detect a pulse, hence the name pulsar. The pulses arrive with extraordinary regularity. The Crab pulsar, formed in the supernova observed in 1054 AD, rotates 30 times per second. The fastest pulsar known, PSRJ 1748-2446 AD, discovered in 2006, rotates 716 times per second, so fast that its equator is moving at about 24% of the speed of light. At these rotation rates, the neutron star bulges significantly at its equator but holds together through its tremendous gravitational binding and the strength of neutron-degenerate matter. Pulsars gradually slow down over millions of years as their magnetic fields radiate energy and carry away angular momentum. The rate of slowdown reveals the pulsar's age and magnetic field strength. Young pulsars like the Crab slow down noticeably over human timescales. The Crab's rotation period increases by about 38 nanoseconds per day. Old pulsars slow down much more gradually and eventually become too slow to generate detectable pulses, though the neutron star continues existing as a dark, cooling ember. Some neutron stars are born with even stronger magnetic fields, up to 1,000 times more intense than typical pulsars, reaching magnetic field strengths of 10 to the 15th Gauss. These objects are called magnetars, and they're the strongest magnets in the universe. At these field strengths, quantum mechanical effects become important. The vacuum of space itself becomes polarized by the magnetic field, affecting how light propagates. Atoms become elongated into needle-like shapes. The magnetic field stores so much energy that magnetars occasionally undergo starquakes, sudden rearrangements of the neutron star's crust that release tremendous bursts of X-rays and gamma rays. The magnetar SGR 1806-20 released a giant flare in 2004 that briefly saturated instruments across the solar system despite being 50,000 light-years away. Not all neutron stars become pulsars. If the magnetic field happens to be nearly aligned with the rotation axis, the beams don't sweep across our line of sight, and we don't see pulses. These objects, often called radio-quiet neutron stars, or simply isolated neutron stars, are much harder to detect. They can only be found through their thermal emission. They're hot enough, at temperatures of a few million degrees, to emit X-rays. The Hubble Space Telescope and X-ray observatories have identified several dozen of these isolated neutron stars, though many more certainly exist undetected. Binary systems where a neutron star has a companion star create unique situations. If the companion is a normal star and the orbit is close enough, the neutron star's gravity can pull material from the companion. This material spirals inward through an accretion disk, heating to millions of degrees and emitting intense X-rays before crashing onto the neutron star's surface. These X-ray binaries can be incredibly luminous, sometimes outshining entire galaxies in X-rays. The infalling material also carries angular momentum, spinning up the neutron star. Over millions of years, an old, slow-spinning pulsar can be recycled into a millisecond pulsar, rotating hundreds of times per second, rejuvenated by mass transfer from its companion. When two neutron stars orbit each other, they form a binary neutron star system. Objects like the Hulse-Taylor binary, discovered by Russell Hulse and Joseph Taylor in 1974, which earned them the 1993 Nobel Prize in Physics. These systems emit gravitational waves, ripples in spacetime that carry away orbital energy, As they lose energy, the neutron stars spiral closer together. Eventually, after millions or billions of years, they merge in a catastrophic collision. The merger produces intense gravitational waves, events that LIGO and other gravitational wave observatories have detected, along with a kilonova, a spectacular explosion that creates heavy elements like gold and platinum through rapid neutron capture. The merger of two neutron stars can produce different outcomes depending on the total mass. If the combined mass is below about 2.2 to 2.9 solar masses, the exact threshold remains uncertain. The merger might create a more massive neutron star, though one that's likely unstable and will soon collapse. If the total mass exceeds this threshold, the merger immediately creates a black hole, with no stable neutron star phase at all. The LIGO detection in 2017, designated GW170817, appears to have created either a hypermassive neutron star that collapsed within seconds or a black hole directly. If the collapsing core of a supernova exceeds about 2.2 to 3 solar masses, again, the exact threshold depends on the poorly known equation of state of nuclear matter. Neutron degeneracy pressure cannot halt the collapse. Nothing known in physics can support the core against its own gravity. The collapse continues, compressing matter to infinite density at a point called a singularity, surrounded by an event horizon from which nothing can escape. The stellar remnant becomes a black hole. The supernova explosion might proceed normally, leaving a black hole at the center of the expanding debris. Or if the core is sufficiently massive, the collapse might be so catastrophic that it swallows the infalling material before an explosion can develop, creating a black hole with little or no visible supernova, a so-called failed supernova. Stellar mass black holes created from supernova typically contain 5 to perhaps 20 solar masses. They're invisible except through their gravitational effects and the radiation from material falling into them. In X-ray binary systems, black holes reveal themselves through the extremely energetic X-rays emitted by infalling material, distinguishable from neutron star systems by the absence of pulsations and by the inferred mass. Anything above 3 solar masses cannot be a neutron star and must be a black hole. Some supernova types leave nothing behind at all. Pair instability supernova occur in extremely massive stars, those with initial masses exceeding about 130 solar masses. In the cores of these giants, temperatures and photon energies become so extreme that gamma-ray photons spontaneously convert into electron-positron pairs. This pair production removes pressure support, causing catastrophic collapse and an explosion so violent that the entire star is obliterated. No neutron star, no black hole, just an expanding cloud of debris. These explosions were more common in the early universe, when stars could grow more massive due to lower metallicity, but they might still occur in regions with primordial composition. The observable supernova remnant, the expanding shell of gas and dust, evolves over thousands to tens of thousands of years. Initially, the blast wave plows through the surrounding interstellar medium at thousands of kilometers per second, creating a hot, shock-heated region. The Crab Nebula, the remnant of the 1054 supernova, is still expanding at about 1,500 kilometers per second. The pulsar at its center powers the nebula's glow, creating a wind of relativistic particles that illuminate the expanding gas. Older supernova remnants like the Cygnus Loop, about 10,000 years old, have expanded to hundreds of light years across. The blast wave has slowed to tens of kilometers per second, and the shock is transitioning from adiabatic expansion, where the remnant retains its heat, to radiative expansion, where the shocked gas cools and radiates energy away, creating the delicate filaments visible in optical and X-ray images. Eventually, after perhaps 100,000 years, the remnant merges with the surrounding interstellar medium, its expansion slowing to match the general motion of gas in the galaxy. The enriched material, Oxygen, carbon, silicon, iron, and other elements forged in the star and the explosion mixes into interstellar clouds. These enriched clouds eventually collapse to form new generations of stars and planets, incorporating the elements created by the previous stellar generation. Every atom of oxygen you breathe, every atom of carbon in your body, was created in a star and dispersed by a supernova, later incorporated into the molecular cloud from which the Sun and Earth formed. What's left after a star explodes depends on the fine details of mass, composition, rotation, and magnetic fields, whether the core becomes a neutron star or black hole, whether the neutron star becomes an observable pulsar or remains radio quiet, whether the magnetic field is ordinary or reaches magnetar strength. Each stellar death creates a unique remnant, a compact object encoding in its properties the history of the parent star and the violence of its death, objects that will persist for trillions of years after the last stars have formed, cooling slowly in the expanding universe, monuments to stellar death that simultaneously mark endings and beginnings in the grand cycle of cosmic recycling. What comets are really made of? Comets have captivated human imagination for millennia, appearing in the sky as ghostly visitors with long tails that stretch across the heavens. Ancient civilizations often viewed them as omens or messengers from the gods. But these cosmic wanderers are not supernatural phenomena. They're physical objects composed of specific materials that reveal the history of the solar system's formation. Understanding what comets are made of means understanding some of the most pristine, unchanged matter left over from the birth of our planetary system billions of years ago. The core of every comet is its nucleus, a solid chunk of ice and rock that can range from a few hundred meters to tens of kilometers across. In 1950, astronomer Fred Whipple proposed what became known as the dirty snowball model of comets, suggesting that comet nuclei were mixtures of ice and dust. This model has proven remarkably accurate, though modern observations have revealed that comets might be better described as icy dirt balls. They contain more rock and dust than Whipple initially thought, sometimes with dust making up 50% or more of their mass. The ice in a comet is primarily water ice, frozen solid at the incredibly cold temperatures found in the outer solar system. But comets contain more than just frozen water. They also harbour other volatile compounds, substances that evaporate at relatively low temperatures. Carbon monoxide ice exists in comet nuclei, freezing at temperatures even lower than water. Carbon dioxide, frozen into dry ice, is abundant in many comets. Methane, ammonia, formaldehyde, methanol, and hydrogen cyanide have all been detected in comets, creating a chemical inventory that reads like an exotic mixture of the simplest molecules that carbon, nitrogen, and oxygen can form when combined with hydrogen. These volatile compounds exist as ices throughout the comet's interior when it's far from the Sun, creating a porous, fluffy structure rather like hard frozen snow. The density of comet nuclei is remarkably low, typically less than water, around 0.6 grams per cubic centimetre. This low density reveals that comets are not solid blocks of ice, but rather loosely consolidated collections of icy particles with substantial void space between them. Picture a pile of snowballs loosely stuck together rather than a single solid block of ice, and you have a reasonable mental image of a comet's internal structure. Mixed throughout this icy matrix are dust particles, tiny grains of rock and organic material. These dust grains are incredibly small, typically measured in micrometers, smaller than the width of a human hair. They're composed of silicates similar to the minerals found in Earth's rocks, compounds of silicon and oxygen mixed with elements like magnesium and iron. Some grains are pure carbon, forming soot-like particles. Others are complex mixtures of organic molecules, carbon-based compounds that include some of the building blocks of life. The organic material in comets is particularly fascinating. When spacecraft have analysed comets up close, or when laboratories have examined samples collected from comet tails, they've found complex organic molecules, including amino acids, the building blocks of proteins, and nucleobases, components of DNA and RNA. These molecules don't indicate that comets harbour life, but they demonstrate that the chemical precursors necessary for life can form naturally in space and were present in the early solar system. Some scientists have proposed that comets bombarding the early Earth might have delivered substantial quantities of organic molecules and water, potentially contributing to the origins of life on our planet. The European Space Agency's Rosetta mission, which orbited and studied Comet 67P/Churyumov-Gerasimenko from 2014 to 2016, provided unprecedented detail about comet composition. The Philae lander, which touched down on the comet's surface, detected 16 organic compounds as the comet's warmth released them from the ice. Among these were 4 compounds never before detected on a comet, including molecules that can act as precursors to amino acids. The comet's surface appeared darker than coal, with a reflectivity of only about 6%, due to the dark organic compounds mixed with the ice. When a comet approaches the Sun, solar heating begins to affect its structure. At distances beyond about 5 astronomical units, 5 times the Earth-Sun distance, roughly Jupiter's orbit, a comet remains frozen and inert. But as it moves closer, sunlight warms the surface. The most volatile ices, like carbon monoxide and carbon dioxide, begin to sublimate, transforming directly from solid to gas without passing through a liquid phase. This sublimation creates pressure beneath the surface, and when that pressure becomes strong enough, gas bursts through the surface, carrying dust particles along with it. These jets of gas and dust create the coma, the glowing atmosphere that surrounds the nucleus and makes the comet visible from Earth. The coma can grow to enormous sizes, sometimes exceeding the diameter of Jupiter, even though the nucleus producing it might be only a few kilometers across. The gas molecules in the coma, particularly water vapor, are broken apart by solar ultraviolet radiation, creating a complex chemistry. Hydroxyl radicals, hydrogen atoms, oxygen atoms, and other fragments fluoresce in sunlight, emitting light at specific wavelengths that give the coma its greenish or bluish tint. The dust released from the comet creates a dust tail, pushed away from the Sun by radiation pressure, the physical push that photons exert when they strike and reflect off particles. This dust tail typically appears yellowish-white because it's sunlight reflecting off dust particles. The tail can extend for millions of miles, creating the spectacular displays visible from Earth. A separate ion tail, composed of ionized gas molecules, is pushed by the solar wind rather than radiation pressure. The ion tail glows with its own light as the ionized molecules fluoresce, often appearing blue due to emissions from ionized carbon monoxide. This ion tail points directly away from the Sun, shaped by the magnetic fields carried in the solar wind. The nucleus itself undergoes changes as the comet repeatedly approaches the Sun. Each passage evaporates a layer of ice from the surface, typically removing a few meters of material per orbit for comets that pass close to the Sun. As the ice sublimates, some dust particles escape with the gas, but others fall back to the surface, gradually building up a layer of dust and larger rock fragments. Over many orbits, this can create a crust of non-volatile material covering the underlying ice, insulating it from solar heating. Some old comets develop such thick crusts that they become inactive, no longer producing visible comas or tails, even when they approach the Sun. NASA's Deep Impact mission in 2005 deliberately crashed a copper impactor into Comet Tempel 1 to excavate beneath the surface and observe the fresh material. The impact created a crater and ejected plumes of material that spectroscopic analysis revealed to be rich in water ice mixed with organic compounds and fine dust. The material beneath the surface appeared similar to, but slightly richer in ice than the surface material, confirming that the interior retains more pristine composition while the surface becomes processed by solar heating. The ratio of different isotopes in comet materials provides clues about where and when they formed. Deuterium, a heavy isotope of hydrogen with an extra neutron, exists in different ratios to normal hydrogen depending on the temperature at which water formed. Measurements of the deuterium to hydrogen ratio in various comets have shown considerable variation, suggesting that comets formed in different regions of the early solar system or at different times. Some comets have deuterium ratios similar to Earth's oceans, while others differ substantially, helping scientists understand whether comets could have delivered Earth's water. The dust particles in comets are themselves diverse and complex. Some grains are crystalline, showing that they formed at high temperatures, possibly near the young sun, then were transported outward and incorporated into comets forming in the cold outer solar system. Other grains are amorphous, formed at low temperatures in the outer reaches. This mixture indicates that the solar nebula was not a static, orderly system, but rather a dynamic environment with extensive mixing, where materials formed in the hot inner regions could be transported outward, and vice versa. Comets also contain tiny pre-solar grains, particles that formed around other stars before the Sun existed and survived incorporation into our solar system. These grains have isotopic compositions distinctly different from solar system materials, marking them as true interstellar visitors preserved within comets. They're typically only nanometers to micrometers in size, but they're extraordinarily valuable because they provide samples of stars that lived and died before our solar system formed, preserved in these frozen time capsules. When comets break apart, as they sometimes do when tidal forces or internal pressure cause the nucleus to fragment, the exposed interior shows the layered structure built up over billions of years. Some regions are richer in ice, others in dust. Some layers contain different mixtures of volatile compounds. These variations likely reflect changes in conditions in the solar nebula as the comet grew by accumulation, recording the changing composition of material in the comet-forming region over time. The darkening of comet surfaces producing the surprisingly low reflectivity observed by Rosetta and other missions results from the organic compounds being altered by solar radiation and cosmic rays. This radiation processing, called space weathering, gradually darkens and reddens the surface materials over time. The very dark surfaces of comet nuclei tell us they've been exposed to space for long periods, accumulating radiation damage that has transformed the original icy material into a darker, more complex mixture. Comets are messengers from the outer solar system, preserving materials that have remained largely unchanged for over 4 billion years. While planets have been geologically active, melting and reforming their materials countless times, and asteroids have been heated and altered, comets have remained frozen in the deep cold of the outer solar system, maintaining their original composition. They're samples of the primordial solar nebula, the disk of gas and dust from which the planets formed, carrying within their icy matrices the water, organic molecules, and mineral grains that were present at the dawn of the planetary system, offering glimpses into the raw materials from which everything in our solar system, including Earth and ultimately life itself, was constructed. The universal laws that would shape all life. While alien life might look nothing like Earth's organisms, using different chemistry, different genetic molecules, different metabolic pathways, certain fundamental principles would constrain and shape all life everywhere in the universe. These universal laws arise not from biological specifics, but from physics, chemistry, thermodynamics, and information theory, disciplines that operate identically throughout the cosmos. Understanding these universal constraints reveals what all life, no matter how alien, must have in common, and what fundamental challenges every living system must solve to exist, grow, reproduce, and evolve on any world, under any star, in any galaxy. The laws of thermodynamics govern all physical processes, and life is no exception. The second law of thermodynamics states that entropy, disorder, tends to increase in closed systems. Left to themselves, organized structures break down, concentrated energy disperses, and order gives way to chaos. A sandcastle erodes, a hot cup of coffee cools to room temperature. Complex molecules break apart into simpler ones. This universal tendency toward disorder creates life's fundamental challenge. Living organisms are highly organized, low-entropy systems existing in a universe that constantly pushes toward disorder. Maintaining biological organization requires constant energy input to fight against entropy's relentless pull. All life, everywhere in the universe, must extract energy from its environment and use that energy to maintain and build ordered structures. On Earth, photosynthetic organisms capture energy from sunlight. Other organisms obtain energy by consuming and metabolizing food, breaking down the chemical bonds in organic molecules and harnessing the released energy. Chemosynthetic organisms extract energy from inorganic chemical reactions. The specific mechanisms vary enormously, but the underlying requirement is universal. Every living thing must have a metabolism, some way of extracting usable energy from its surroundings to power the processes that maintain life. This creates a fundamental constraint. Life can only exist where energy flows. Environments in perfect thermodynamic equilibrium, where no energy gradients exist, cannot support life. Life requires disequilibrium, a hot vent and cold water, sunlight falling on chemical systems, redox gradients between different chemical species. These disequilibria provide the energy flow that life harnesses. Alien life, no matter what chemistry it uses or what planet it inhabits, must exist in regions where energy flows from higher to lower energy states, capturing some of that flowing energy to power metabolism. Evolution through natural selection represents another universal principle. Any system capable of reproduction, variation, and selection will inevitably evolve. This is not a biological principle, but a logical and mathematical necessity. If organisms reproduce, creating copies of themselves, and if those copies are not perfect but contain variations, and if some variants survive and reproduce more successfully than others due to those variations, then the population will change over generations as successful variants become more common and unsuccessful variants decline. This is evolution by natural selection, and it operates on any replicating system with heritable variation subject to selection pressures. Alien life would therefore inevitably evolve, becoming adapted to its environment through countless generations of selection favoring organisms better suited to local conditions. The specific adaptations would differ. Alien organisms might evolve features we've never imagined, but the process would be the same. Evolution is not optional or unique to Earth. It's a fundamental consequence of how replicating systems behave over time. Any civilization that discovers alien life would find that life has been shaped by evolution just as Earth's life has been shaped, even if the resulting organisms look and function completely differently. This evolutionary principle creates a corollary, convergent evolution, where different lineages independently evolve similar solutions to similar problems, occurs because physics and chemistry constrain the possible solutions. Eyes evolved independently many times on Earth because detecting light provides such valuable information, and focusing light onto photosensitive cells is the most effective way to create detailed images. Streamlined body shapes evolved independently in fish, dolphins, ichthyosaurs, and penguins because that shape minimizes drag in water. These convergences occur because physical laws determine what works well in given circumstances. Alien life would show similar convergences. Any organism that needs to move through fluid efficiently would likely evolve some form of streamlined shape, because physics demands it. Any organism that needs to detect electromagnetic radiation would likely evolve some structure that captures and focuses that radiation. The details would vary. Alien eyes might have 10 light-sensing structures instead of 2, might sense infrared instead of visible light, might use completely different photosensitive molecules than Earth organisms. But the basic function would be similar because the physics of light detection operates universally. Information storage and transmission represent another universal requirement. Living organisms must store information about how to build and maintain themselves, and they must transmit this information to their offspring. On Earth, this information is stored in DNA and RNA sequences, but the specific molecule doesn't matter. What matters is that some physical system must encode instructions that can be copied and passed to the next generation, and these instructions must contain enough information to specify the organism's structure and function with sufficient detail that offspring resemble parents. The amount of information required sets minimum limits on the complexity of genetic systems. A viable organism cannot be specified by just a few bits of information. It requires substantial information content to encode even the simplest metabolic pathways, structural components, and reproduction mechanisms. Earth's simplest free-living bacteria have genomes containing roughly 500,000 base pairs, encoding about 500 genes. This represents the approximate minimum information content for independent life under Earth conditions. Alien life might require more or less information, depending on environmental complexity and metabolic strategies, but some minimum threshold exists below which organisms cannot encode enough instructions to function and reproduce reliably. The fidelity of information copying, how accurately genetic information is replicated, creates a universal trade-off. Perfect copying with zero errors would prevent evolution because no variation would arise. But too many copying errors would lead to error catastrophe, where genetic information degrades faster than selection can eliminate harmful mutations. There exists an optimal error rate that balances stability and evolvability, allowing organisms to maintain essential functions while still generating the variation necessary for adaptation. Alien genetic systems would face this same trade-off and would likely evolve error rates in a similar optimal range, regardless of what molecules store their genetic information. Physical scaling laws constrain organism size and structure. The strength of materials scales with cross-sectional area, proportional to the square of linear dimensions, while weight scales with volume, proportional to the cube of linear dimensions. This means that as organisms get larger, their weight increases faster than their structural strength. A human scaled up to 10 times normal height would weigh 1,000 times as much, but would have bones only 100 times as strong. The skeleton would collapse under the weight. This scaling law explains why large land animals have thick, sturdy legs relative to their body size, while small animals have gracile limbs. Elephants have legs like pillars. Mice have delicate, thin legs. An alien planet with higher gravity would have organisms with even thicker, stronger structural supports relative to their size. A lower gravity planet would allow more slender structures. But the mathematics of scaling operates universally, constraining what body plans are physically possible at different sizes. Surface area to volume ratio creates another universal constraint. Small organisms have large surface area relative to their volume, making heat loss rapid and making diffusion effective for transporting materials. Large organisms have small surface area relative to volume, retaining heat more effectively but requiring specialized circulatory systems because diffusion becomes inadequate for transporting nutrients and waste across large distances. These scaling relationships would govern alien life, just as they govern Earth life, determining which transport mechanisms are necessary at different sizes and what thermal regulation strategies are required. Chemical reaction rates depend on temperature, creating universal constraints on metabolism. Higher temperatures speed up chemical reactions exponentially. A rule of thumb is that reactions roughly double in rate for every 10-degree increase in temperature. This means organisms in hot environments can have faster metabolisms, grow more quickly, and potentially think faster if they're intelligent. Organisms in cold environments have slower metabolisms, grow more slowly, and would process information more slowly if conscious. These temperature effects on reaction kinetics are universal, affecting any chemistry-based life regardless of specific biochemistry. Diffusion rates determined by physics limit how large cells can be. Molecules move through cells by random thermal motion, diffusion. This process is slow. A molecule might take seconds or minutes to diffuse across a large cell. This limits cell size because cells need to move nutrients, wastes, and signals around internally, and diffusion becomes prohibitively slow beyond certain sizes. Earth's largest cells are only about 1 millimeter across, and most are much smaller. Alien cells, regardless of their chemistry, would face similar diffusion limits unless they evolved active transport mechanisms, like Earth's eukaryotic cells use, with molecular motors moving cargo along cellular highways. The speed of light creates absolute limits on information transfer. No signal can travel faster than light, which means there are minimum response times for any organism based on its size. An organism the size of a bacterium, a few micrometers, experiences internal light travel times of trillionths of a second, essentially instantaneous. But a hypothetical, planet-sized organism would experience light travel times of tens of milliseconds from one side to the other, creating unavoidable delays in communication and coordination between distant parts. Very large organisms would necessarily be slow to respond to stimuli and might need decentralized control systems because centralized coordination becomes impractical when signal delays become significant. Energy efficiency sets ultimate limits on what metabolic processes are possible. Chemical reactions have maximum energy yields determined by the bonds being broken and formed. An organism cannot extract more energy from a reaction than the chemistry allows. This means life on worlds with limited energy availability, dim stars, deep subsurface environments, chemical poor conditions would necessarily have low-energy lifestyles, growing slowly and reproducing infrequently. High-energy environments allow active, energetic lifestyles, but also demand mechanisms to dissipate excess heat. Water's unique properties, while not absolutely required for life, make it an excellent solvent for biochemistry. Water remains liquid across a convenient temperature range, has high heat capacity that buffers against temperature changes, expands when freezing so ice floats, acts as a polar solvent that dissolves ions and many organic molecules, and participates in many biochemical reactions. While life could potentially use other solvents, liquid ammonia, methane, supercritical carbon dioxide, any solvent must have properties that allow complex chemistry to occur, molecules to dissolve and interact, and cellular compartments to form. Not many liquids have the right combination of properties, making water-based life probably more common than exotic alternatives, though not exclusively so. Complexity emerges hierarchically, with simple components combining into more complex structures, which combine into still more complex systems. Atoms form molecules. Molecules form macromolecules. Macromolecules form cellular structures. Cells form tissues. Tissues form organs. Organs form organisms. Organisms form ecosystems. This hierarchical organization seems to be how complexity arises universally, because building complex systems directly from simple components becomes unmanageable beyond certain complexity levels. Modular, hierarchical construction allows greater complexity to be achieved and maintained. Alien life would likely show similar hierarchical organization, even if the specific components at each level differ completely from Earth's biological hierarchy. Darwinian selection favors efficiency. Organisms that use resources more efficiently have advantages over wasteful competitors. This drives evolution toward optimized solutions within physical constraints. Alien life would similarly be shaped by selection for efficiency, though what constitutes efficient depends on environmental context. In energy-rich environments, speed might matter more than efficiency. In energy-poor environments, extreme efficiency becomes essential for survival. But the general principle that natural selection tends to optimize organisms for their specific circumstances within physical constraints operates universally. The universal laws that would shape all life encompass thermodynamics, demanding that life exist only where energy flows, and that organisms extract energy to maintain order against entropy. Evolution, through natural selection, being an inevitable consequence of imperfect replication with variation. Information requirements, setting minimum complexity thresholds, scaling laws constraining size and structure, chemical kinetics determining metabolic rates, and physical limits on signal speeds, and diffusion rates imposing fundamental constraints on how large and fast organisms can be. These laws operate identically throughout the universe, guaranteeing that while alien life might look and function completely differently from Earth's organisms in countless details, the fundamental principles governing life's existence, evolution, and physical limitations would be the same everywhere, creating a common framework that all life must operate within, regardless of whether it's based on carbon or silicon, DNA or something entirely different, oxygen metabolism or sulfur chemistry. Because physics and chemistry and thermodynamics and information theory operate identically on every world orbiting every star in every galaxy, creating universal constraints that shape all possible forms of life into entities that must harvest energy, maintain organization, store and transmit information, and evolve through selection, making these principles the true universals of biology that would apply to any living thing humans might ever encounter. The lighthouse stars that spin incredibly fast. In 1967, a graduate student named Jocelyn Bell noticed something peculiar in her radio telescope Delta, a signal that pulsed with extraordinary regularity, repeating every 1.3373 seconds. The precision was so remarkable that she and her advisor initially wondered whether they had detected an artificial signal from an extraterrestrial civilization. They jokingly called it LGM-1 for Little Green Men. But as more of these pulsing sources were discovered, each with its own precise period, it became clear they were witnessing something natural, but entirely unexpected. Rapidly spinning neutron stars whose beams of radiation sweep across Earth like cosmic lighthouses. These objects, now called pulsars, are among the most extreme objects in the universe. They are neutron stars, the collapsed cores of massive stars that exploded as supernova, compressed to densities where a sugar cube-sized amount of material would weigh as much as a mountain. What makes pulsars special is not just their incredible density, but their rotation. These stars spin at rates that seem impossible for something so massive. Many complete one rotation in less than a second, some in mere milliseconds, whirling around hundreds of times per second while containing more mass than the Sun. The story of a pulsar begins with the death of a massive star. When a star, at least 8 times more massive than the Sun, exhausts its nuclear fuel, its core collapses catastrophically. The outer layers rebound and explode outward as a supernova, but the core continues collapsing until nuclear forces halt the compression, creating a neutron star about 12 miles across. This neutron star inherits the angular momentum of the original star's core, but because the radius has shrunk by a factor of perhaps 100,000, the rotation rate increases dramatically through conservation of angular momentum. Imagine a figure skater pulling their arms inward during a spin, rotating faster and faster as their radius decreases. The collapsing stellar core undergoes the same process, but on a far more extreme scale. A star that was rotating once every few weeks might produce a neutron star that rotates several times per second. The fastest spinning pulsar known, designated PSRJ 1748-2446 AD, rotates 716 times per second. At its equator, the surface is moving at approximately 70,000 miles per second, nearly 1/4 the speed of light. At these speeds, the neutron star is ablate, bulging significantly at its equator due to centrifugal forces, yet it holds together through the tremendous strength of neutron degenerate matter and its own crushing gravity. The lighthouse effect that makes pulsars detectable comes from their magnetic fields. Neutron stars possess the strongest magnetic fields known in the universe, typically 1,000,000,000,000 times stronger than Earth's magnetic field. When the core of the parent star collapses, any magnetic field present is compressed and amplified tremendously. This field doesn't simply shrink, it gets concentrated into a much smaller volume, intensifying to values that would tear apart atoms and polarize the vacuum of space itself. This intense magnetic field is not aligned with the neutron star's rotation axis. Just as Earth's magnetic poles don't coincide with its geographic poles, a neutron star's magnetic axis is typically tilted relative to its spin axis. Charged particles, primarily electrons and positrons, are accelerated along the magnetic field lines, particularly near the magnetic poles. These particles, accelerating at relativistic speeds, emit intense beams of radiation through a process called synchrotron radiation. The beams emerge from the magnetic poles, creating two searchlights that sweep through space as the neutron star rotates. When one of these beams sweeps across Earth, we detect a pulse of radio waves, X-rays, or gamma rays, depending on the pulsar's characteristics. The pulse arrives with extraordinary regularity. The best pulsars keep time as accurately as atomic clocks, varying by only microseconds over years. This precision exists because the neutron star is such a stable rotator. Its enormous rotational inertia, combined with its extreme density and rigidity, means that nothing can easily change its spin rate. It's like an enormous cosmic flywheel, storing vast amounts of rotational energy and releasing it only very gradually. The radio emission mechanism is complex and still not completely understood, despite decades of study. The acceleration of charged particles near the magnetic poles creates a cascade of electromagnetic radiation. These particles follow the curved magnetic field lines, and as they accelerate, they emit photons. These photons can interact with the intense magnetic field to create more particle-antiparticle pairs, which then accelerate and create more photons, building up a cascade that produces the intense radio emission we detect. The region where this occurs, just above the magnetic poles, is called the polar cap, and it's here that the lighthouse beams originate. Not all pulsars emit at the same wavelengths. Some are primarily radio pulsars, detected through their radio emission. Others are X-ray pulsars, emitting primarily high-energy X-rays. A few emit gamma rays, the most energetic form of electromagnetic radiation. Some pulsars emit across the entire electromagnetic spectrum simultaneously, creating pulses detectable from radio waves through gamma rays. The emission properties depend on factors like the neutron star's age, its magnetic field strength, its rotation rate, and the environment surrounding it. Young pulsars, recently formed in supernova explosions, tend to rotate faster and have stronger magnetic fields than old pulsars. The Crab pulsar, formed in a supernova observed by Chinese astronomers in 1054 AD, rotates 30 times per second and emits powerfully across the electromagnetic spectrum. It sits at the center of the Crab Nebula, the expanding remnant of that supernova explosion, and its intense radiation illuminates the surrounding nebula, causing it to glow. The pulsar acts like a cosmic power station, converting its rotational energy into electromagnetic radiation and high-energy particles that energize the nebula. Pulsars slow down over time, gradually losing rotational energy. This spin-down occurs because the rotating magnetic field acts like a brake. The magnetic field lines extend far into space, and as they rotate with the neutron star, they drag charged particles along, accelerating them and carrying away energy and angular momentum. This magnetic braking gradually robs the neutron star of its rotational energy. A young pulsar might slow down measurably over just a few years, while an old pulsar might take millions of years to show detectable changes in its period. The rate at which a pulsar slows down reveals information about its magnetic field strength and age. By measuring the current rotation period and the rate of change of that period, astronomers can estimate how long the pulsar has been spinning down and how much longer it will continue to pulse before its rotation becomes too slow and its magnetic field too weak to generate detectable radiation. Most pulsars have lifetimes of tens of millions of years as active radio sources before they fade from detectability, though the neutron star itself continues existing and spinning, just no longer producing observable pulses. Some pulsars experience sudden speed-ups, called glitches. The neutron star's rotation rate, which normally decreases steadily, suddenly increases slightly, then resumes its gradual slowdown. These glitches are thought to occur because the neutron star's interior contains a superfluid, a state of matter with zero viscosity that can flow without any resistance. This superfluid rotates faster than the star's crust, and occasionally, angular momentum transfers suddenly from the superfluid to the crust, causing the observable spin-up. Glitches provide rare windows into the exotic physics occurring inside neutron stars, where matter exists in states impossible to recreate in laboratories. Millisecond pulsars present a fascinating puzzle. These pulsars rotate hundreds of times per second, far faster than young pulsars, yet they're old neutron stars, billions of years old. How can an old pulsar be spinning so fast? The answer lies in a process called recycling. A millisecond pulsar was once a normal pulsar that slowed down over hundreds of millions of years. But if it's in a binary system with a companion star, and that companion evolves to become a giant star, matter can flow from the companion onto the neutron star. This infalling matter carries angular momentum, spinning up the neutron star like water hitting a water wheel. Over millions of years, the neutron star is spun up to millisecond periods, recycled into a new youth of rapid rotation. Some pulsars are part of binary systems where we can directly observe this process happening. X-ray binary pulsars show X-ray pulses as the neutron star accretes material from its companion. The infalling material, heated to millions of degrees before hitting the neutron star's surface, emits intense X-rays. These systems are the evolutionary precursors to millisecond pulsars, caught in the act of being spun up by accretion. The most rapidly rotating pulsars ever discovered are all millisecond pulsars, and some of them are in dense globular clusters where stars are packed closely together. The high stellar density in these clusters makes binary interactions more likely, creating environments where many neutron stars can be recycled through accretion. Some globular clusters contain dozens of millisecond pulsars, creating a cosmic percussion section where numerous neutron stars pulse at different rates, each one a precisely ticking clock with its own unique period. Pulsars can also have planets. The first exoplanets ever discovered orbit a pulsar called PSRB 1257 + 12. These planets were detected through tiny variations in the pulsar's timing. As the planets orbit, their gravity tugs the pulsar slightly back and forth, causing the pulses to arrive slightly early or late in a periodic pattern. The planets orbiting this pulsar are thought to be second-generation worlds, formed from the debris of the supernova explosion that created the neutron star, or possibly from material that later fell back onto the system. These are harsh worlds, bathed in intense radiation from the pulsar, utterly unlike the planets orbiting normal stars. Binary pulsars, where two neutron stars orbit each other, provide extraordinary laboratories for testing general relativity. The orbital motion of such systems produces gravitational waves that carry away energy, causing the orbit to shrink over time. The rate of orbital decay matches Einstein's predictions with incredible precision. The first binary pulsar discovered, PSRB 1913+16, provided the first indirect evidence for gravitational waves. Decades before, gravitational wave detectors directly observed them from merging black holes and neutron stars. The regularity of pulsar timing has practical applications. Astronomers use networks of millisecond pulsars across the galaxy as a cosmic timing array, watching for tiny correlated deviations in their pulse arrival times that would indicate gravitational waves passing through the galaxy. These pulsar timing arrays are sensitive to gravitational waves with much longer wavelengths than ground-based detectors can observe, potentially detecting the gravitational wave background from supermassive black hole mergers throughout the universe. Pulsars also serve as natural laboratories for extreme physics. The conditions near their surfaces, intense magnetic fields, extreme gravity, densities exceeding that of atomic nuclei, cannot be reproduced on Earth. By observing pulsars across the electromagnetic spectrum and measuring their properties precisely, physicists learn about how matter behaves under conditions that push the boundaries of our physical theories, testing general relativity in strong gravitational fields and probing the equation of state of matter at nuclear densities. These spinning neutron stars, these cosmic lighthouses flashing their beams across the universe, represent one endpoint of stellar evolution. From the violent collapse of a massive star's core emerges an object so dense, so rapidly spinning, so strongly magnetized that it challenges our understanding of physics. Each pulse detected from a pulsar is a message from one of the universe's most extreme environments, a precisely timed signal carrying information about physics at the edge of what's possible, reminding us that the universe contains objects and phenomena far stranger than we could have imagined before we discovered these remarkable, spinning stellar remnants. The extreme environments where life could thrive. Life on Earth exists in places that seem utterly hostile to survival, in boiling hot springs where water approaches its boiling point, in frozen Antarctic lakes where temperatures remain below zero year-round, in crushing depths of the ocean where pressure would flatten most organisms instantly, in intensely acidic pools that would dissolve metal, and in radioactive waste sites where radiation levels would kill a human in hours. These extreme environments, once thought to be sterile and lifeless, actually teem with organisms called extremophiles, life forms that not only survive but thrive in conditions that would destroy most familiar creatures. Understanding where these extremophiles live and how they manage to exist in such harsh conditions reveals that life's possibilities extend far beyond the comfortable, temperate zones we associate with habitability, suggesting that alien life might flourish in environments throughout the universe that we would never have considered searching. Temperature extremes represent one of the most dramatic challenges for life. At Yellowstone National Park and similar geothermal areas worldwide, hot springs reach temperatures near or even above the boiling point of water. In these scalding pools, organisms called thermophiles and hyperthermophiles thrive at temperatures that would cook most life forms. Some bacteria live comfortably at temperatures around 180 degrees Fahrenheit, and certain archaea, single-celled organisms, distinct from bacteria, can survive and reproduce at temperatures exceeding 230 degrees Fahrenheit in superheated water under pressure that prevents it from boiling. These heat-loving organisms have specialized proteins that maintain their structure at high temperatures instead of denaturing and unfolding like normal proteins would. Their cell membranes contain special lipids that remain fluid and functional at temperatures where ordinary membranes would fall apart. Their DNA includes protective mechanisms that prevent the double helix from separating under thermal stress. Every aspect of their biochemistry has been optimized through evolution to function at temperatures that would destroy conventional life in seconds. The existence of thermophiles suggests that life could exist in hot environments throughout the solar system and beyond, in volcanic hot springs on Mars, in heated cracks near lava flows on Jupiter's moon Io, or in the scalding oceans of planets closer to their stars than Earth is to the Sun. At the opposite extreme, psychrophiles, cold-loving organisms, thrive at temperatures well below the freezing point of pure water. In Antarctica, microbes live in lakes that remain liquid beneath ice, because salt lowers the freezing point, maintaining temperatures around -5 to -20 degrees Fahrenheit. These organisms produce antifreeze proteins that prevent ice crystals from forming inside their cells, manufacture enzymes that remain flexible and functional at temperatures where normal enzymes become rigid and useless, and slow their metabolisms to conserve energy in the cold. Some bacteria found in permafrost remain viable after being frozen for hundreds of thousands of years, suggesting remarkable cold tolerance. The discovery of psychrophiles revolutionized thinking about where life could exist in the solar system. Europa, Jupiter's ice-covered moon, has a liquid ocean beneath miles of surface ice, kept liquid by tidal heating from Jupiter's gravity. The water at the bottom of this ocean, near Europa's rocky core, might be relatively warm, perhaps just above freezing, and could host psychrophilic life adapted to darkness and cold. Enceladus, Saturn's small moon, shoots geysers of liquid water through cracks in its ice shell, water that comes from a subsurface ocean. Despite the frigid surface temperature of -330 degrees Fahrenheit, the ocean beneath remains liquid, warmed by tidal forces. Life in these hidden oceans would need to tolerate extreme cold, total darkness, and high pressure, but Earth's psychrophiles prove that temperature alone doesn't preclude life. Pressure creates another extreme that life has conquered remarkably. In the Mariana Trench, the deepest part of Earth's oceans, pressure reaches about 16,000 pounds per square inch, more than 1,000 times atmospheric pressure at sea level. This crushing pressure would compress gases, alter protein structures, and collapse air-filled spaces in ordinary organisms. Yet the trench is inhabited by fish, amphipods, bacteria, and other creatures specifically adapted to extreme pressure. These organisms have no air-filled swim bladders that would collapse. Their proteins are stabilized by special amino acid sequences and by molecules called piezolites that counteract pressure's effects on molecular structure. Their cell membranes contain unsaturated fatty acids that remain fluid under pressure instead of becoming rigid. The existence of barophils, pressure-loving organisms, suggests that life could exist in the high-pressure environments found deep within planets and moons. The subsurface oceans of Europa and Enceladus experience significant pressure from the weight of overlying ice. The deeper regions of these oceans, near the rocky seafloor, would experience pressures far exceeding anything at Earth's surface. Yet if Earth organisms can adapt to pressures in the Mariana Trench, alien organisms might adapt to even higher pressures in alien oceans. Some scientists even speculate about life existing in the liquid metallic hydrogen regions deep within gas giants like Jupiter, though the extreme temperatures and pressures there would require biochemistry completely unlike anything on Earth. Acidity represents another extreme environment where life flourishes. Highly acidic environments with pH levels below 3, comparable to battery acid or stomach acid, would dissolve most biological molecules and disrupt normal cellular processes. Yet acidophiles thrive in such conditions. Iron Mountain in California hosts drainage from abandoned mines with pH levels below 0, more acidic than concentrated sulfuric acid. Despite this extreme acidity, bacteria and archaea live in these toxic streams, deriving energy from oxidizing iron and sulfur. These organisms maintain neutral pH inside their cells while existing in incredibly acidic environments, pumping protons out of their cells faster than the acidic environments can push them in, a process that requires substantial energy but allows survival in places nothing else can tolerate. At the opposite extreme, alkalophiles live in highly alkaline environments, with pH levels above 9 or even above 11. Soda lakes like Mono Lake in California and Lake Magadi in Kenya have pH levels around 10, nearly as caustic as bleach. Microorganisms in these lakes have adapted to maintain their internal chemistry despite the harsh external conditions, using specialized proteins and transport mechanisms to survive. The existence of life in both extremely acidic and extremely alkaline environments suggests that pH is a challenge life can overcome through evolution, expanding the range of potentially habitable environments to include caustic lakes and springs on other worlds. Salinity creates osmotic stress that would kill most organisms. Normal cells placed in very salty water lose water through osmosis and shrivel up. Yet halophiles, salt-loving organisms, thrive in hypersaline environments like the Dead Sea, where salt concentration exceeds 30%, and in salt evaporation ponds, where salt approaches saturation. Some archaea not only tolerate but require high salt concentrations to survive. They accumulate potassium and other ions inside their cells to balance the external salt concentration, preventing osmotic water loss. Their proteins are specifically adapted to function in high salt conditions and would actually denature and unfold in normal salt concentrations. Hypersaline environments might exist on Mars, where briny water could remain liquid at temperatures below the freezing point of pure water. Salts detected on Mars's surface could create localized regions where salty water exists seasonally or sporadically. If life ever existed on Mars, or if it exists there today, it might persist in these briny environments, sheltered from the planet's coal-thin atmosphere by adaptation similar to Earth's halophiles. Radiation represents one of the most challenging extremes. Ionizing radiation damages DNA, breaks apart molecules, and creates reactive free radicals that wreak havoc on cellular chemistry. Yet radio-resistant organisms can survive radiation doses thousands of times higher than would be lethal to humans. The bacterium Deinococcus radiodurans can withstand radiation exposure of several million rads, enough to shatter its DNA into hundreds of fragments and completely repair its genome within hours, reconstituting functional chromosomes from the pieces. This organism accumulates high concentrations of manganese compounds that protect its cellular machinery from radiation damage and possesses redundant copies of its genome, along with extraordinarily efficient DNA repair mechanisms. The discovery of radio-resistant life expands possibilities for life in high radiation environments throughout the universe. Mars's surface experiences high radiation levels because Mars lacks a strong magnetic field and thick atmosphere to shield the surface from cosmic rays and solar radiation. Any surface life on Mars would need radiation resistance. The moons of Jupiter, particularly Europa, exist within Jupiter's powerful radiation belts and experience intense radiation bombardment. Life in Europa's subsurface ocean would be shielded by miles of ice, but any organism near the surface would need extreme radiation tolerance. Desiccation, extreme dryness, challenges life by removing the water necessary for biochemical reactions. Yet xerophiles can survive in nearly waterless environments. Microorganisms have been found in the driest deserts on Earth, in salt crystals, and even in the upper atmosphere. Some organisms, like tardigrades, microscopic animals also called water bears, can enter a state called cryptobiosis when they dry out. In this state, they replace water in their cells with protective molecules like trehalose sugar, essentially turning into a glass-like solid that can survive for years or decades without water, then rehydrate and resume normal activity when water becomes available again. The ability to survive desiccation suggests that life could persist in extremely dry environments like Mars, where liquid water is rare and exists only transiently. Organisms in a cryptobiotic state could wait through long dry periods, potentially centuries or longer, then reactivate during brief periods when liquid water appears. This strategy might allow life to survive, even on worlds where habitable conditions are rare and sporadic rather than continuous. Oligotrophs thrive in nutrient-poor environments where most life would starve. These organisms can extract energy and nutrients from resources that seem impossibly limited. Some bacteria derive energy from oxidizing trace amounts of hydrogen gas or from reducing tiny concentrations of metal ions. Others grow incredibly slowly, dividing perhaps once per century or even less frequently, living at the absolute minimum energy budget that can sustain life. These organisms survive in deep subsurface rocks, in ultra-pure cave water, and in nutrient-depleted ocean regions. The existence of oligotrophs suggests that life could persist in environments throughout the universe that seem too resource-poor to support metabolism. Deep beneath the surfaces of planets and moons, in the pores between rock grains, organisms might eke out existence on trace amounts of hydrogen from water-rock reactions, or on the minimal nutrients leached from minerals over geological timescales. This greatly expands the potential volume of habitable space, not just surfaces and oceans, but the entire crustal volume of rocky worlds down to depths where temperature becomes prohibitive. Some of the most extreme environments on Earth combine multiple stresses. Hydrothermal vents on the ocean floor experience high temperature, high pressure, high concentrations of toxic metals and sulfur compounds, and complete darkness. Yet these vents support thriving ecosystems based on chemosynthetic bacteria that extract energy from chemicals spewing from the vents. Hot acidic springs combine high temperature with extremely low pH. Ice-covered Antarctic lakes combine extreme cold with high salinity and seasonal or permanent darkness. Life found in these multi-stress environments proves that organisms can adapt to simultaneous challenges, not just single extremes. This ability to tolerate multiple stresses simultaneously is crucial for evaluating habitability on alien worlds, where conditions often involve several challenges at once. Europa's ocean experiences cold, pressure, darkness, and possibly high salinity, all at the same time. Mars's surface experiences extreme cold, desiccation, high radiation, and low pressure simultaneously. Venus's clouds experience high acidity, moderate temperature, and the presence of sulfuric acid droplets. Each of these environments might seem impossibly hostile when considered as a whole, but examining them as combinations of specific stresses that Earth organisms have individually overcome makes them seem more potentially habitable. The extremophiles of Earth demonstrate that life is far more flexible and resilient than once thought. Organisms have evolved mechanisms to survive and thrive in virtually every environment on Earth where liquid water exists, at least transiently, and where some source of chemical energy is available. Temperature, pressure, acidity, salinity, radiation, desiccation, each extreme that seems to represent an absolute barrier to life, turns out to be merely another challenge that evolution can overcome, given time and the right selection pressures. These discoveries transform our search for life beyond Earth. Rather than looking only for planets with Earth-like conditions, moderate temperature, neutral pH, low radiation, abundant water, we can expand our search to include extreme environments throughout the solar system and beyond. Volcanic hot springs on Mars or Venus, frozen oceans on icy moons, the clouds of Venus, subsurface aquifers deep within asteroids, the hydrothermal systems that might exist beneath the surfaces of large moons. All of these become potential habitats once we recognize that life on Earth already thrives in analogous extremes. The extreme environments where life could thrive extend from the scalding vents of volcanic springs to the frozen lakes of Antarctica, from the crushing depths of ocean trenches to the desiccated rocks of the driest deserts, from intensely acidic mine drainage to alkaline soda lakes, from the radiation-blasted rocks near nuclear waste to the nutrient-depleted waters of remote caves. Each extreme habitat on Earth hosts specialized organisms that have turned hostile conditions into homes through remarkable biochemical and physiological adaptations, proving that life's potential territory extends far beyond the comfortable middle ground to encompass nearly anywhere liquid exists, energy flows, and raw materials can be found, vastly expanding the cosmic real estate where life might emerge and flourish across the universe. The chemistry required for life beyond Earth. Life at its most fundamental level is chemistry. Every thought you think, every breath you take, every movement you make results from chemical reactions occurring in your cells. Molecules bind together and break apart. Energy flows from one form to another. And through countless chemical transformations, inanimate matter becomes animate. Dead molecules become living organisms. Understanding what chemistry is required for life beyond Earth means understanding what makes life possible at all. The elements, the reactions, the solvents, and the energy sources that could allow chemistry to cross the threshold from complex but lifeless reactions into something that grows, reproduces, evolves, and ultimately builds civilizations among the stars. Carbon stands at the center of all known life. Every organism on Earth, from bacteria to blue whales, builds its body from carbon-based molecules. Carbon's unique properties make it extraordinarily suitable for life. Each carbon atom can form 4 chemical bonds with other atoms, allowing it to create an immense diversity of molecular structures, long chains, branching trees, rings, and complex 3-dimensional shapes. Carbon bonds with itself strongly enough to create stable molecules, but not so strongly that the bonds cannot be broken and rearranged through normal chemical reactions. This balance allows carbon molecules to be both stable enough to maintain structure and reactive enough to participate in the constant chemical transformations that life requires. Organic chemistry, the chemistry of carbon compounds, encompasses millions of known molecules and potentially billions more that could exist. Carbon combines readily with hydrogen, oxygen, nitrogen, sulfur, and phosphorus to create the molecules of life. Proteins, the workhorses of cells that catalyze reactions and build structures, are chains of amino acids linked together, each amino acid containing carbon, hydrogen, oxygen, and nitrogen. DNA and RNA, which store and transmit genetic information, are built from carbon-containing sugars, phosphate groups, and nitrogen-rich bases. Lipids, which form cell membranes and store energy, are long carbon chains with various functional groups attached. Carbohydrates, which provide energy and structural support, are carbon molecules with hydrogen and oxygen in specific ratios. But is carbon truly necessary for life, or is it simply the element that happened to work on Earth? Silicon, sitting directly below carbon in the periodic table, shares many of carbon's properties. Silicon also forms 4 chemical bonds and can create chains and rings similar to carbon. Science fiction has long speculated about silicon-based life, but silicon faces significant challenges. Silicon-silicon bonds are weaker than carbon-carbon bonds, making long silicon chains less stable. Silicon compounds tend to be much less diverse than carbon compounds. While carbon forms millions of different molecules, silicon chemistry is far more limited. Most critically, silicon's most common compound is silicon dioxide, quartz, sand, rock, which is extremely stable and insoluble. When silicon burns with oxygen, it creates solid rock rather than a gas that can be easily expelled and recycled. However, silicon-based life might be possible in environments completely unlike Earth. In extremely cold environments where water is frozen solid, silicon chemistry might become more favorable. In the presence of liquid hydrocarbons instead of water, silicon compounds might behave differently, remaining soluble and reactive rather than precipitating as rocks. A frigid world with seas of liquid methane or ethane, like Saturn's moon Titan, might provide conditions where silicon-based biochemistry could operate. Such life would function on completely different principles than Earth's carbon-based organisms, but it might still meet the basic requirements: complexity, self-replication, evolution, and metabolism. Hydrogen plays a crucial role in biochemistry beyond being part of organic molecules. Hydrogen ions, protons, are essential for energy generation in cells. Earth's organisms create differences in hydrogen ion concentration across membranes, then allow the ions to flow back through specialized proteins called ATP synthase, which harness the flowing ions to create ATP, the universal energy currency of life. This process, called chemiosmosis, powers nearly all life on Earth and represents a fundamental way of coupling energy sources to useful work. Any biochemistry, whether carbon-based or otherwise, would need some mechanism for capturing and storing energy, and hydrogen's simple chemistry makes it an excellent candidate for this role, regardless of the specific biochemistry involved. Oxygen serves multiple roles in Earth's biochemistry. It's part of water, part of most organic molecules, and it serves as the final electron acceptor in cellular respiration, the process by which organisms extract energy from food. When glucose is metabolized with oxygen, the reaction releases large amounts of energy that cells capture in the chemical bonds of ATP. This oxygen-based metabolism, called aerobic respiration, is far more efficient than metabolism without oxygen. However, oxygen was not always available on Earth. For the first 2 billion years or more, Earth's atmosphere contained very little free oxygen, and early life functioned without it, using anaerobic metabolism based on different chemical reactions. Some organisms today still live without oxygen, in deep ocean sediments or the guts of animals, using sulfur compounds, nitrates, or iron as alternatives to oxygen. Life beyond Earth might never develop oxygen-based metabolism if oxygen never becomes abundant in the atmosphere. Planets orbiting red dwarf stars might have difficulty accumulating oxygen because ultraviolet light from the star, which on Earth helps break apart water molecules in the upper atmosphere, leading to oxygen accumulation, is less intense. Life on such worlds might remain dependent on anaerobic metabolism indefinitely, which would likely limit the size and energy consumption of organisms. Active, energy-intensive lifestyles, like those of birds or mammals, require the high energy output that only oxygen metabolism provides. Alien life using alternative metabolic pathways might be restricted to smaller, slower, lower energy forms. Nitrogen is essential for proteins and nucleic acids. It's found in amino acids and in the bases that make up DNA and RNA. Nitrogen chemistry is complex and often difficult. Nitrogen gas in the atmosphere consists of 2 nitrogen atoms triple bonded together, making it very stable and unreactive. Converting atmospheric nitrogen into biologically useful forms, a process called nitrogen fixation, requires significant energy or specialized catalysts. On Earth, certain bacteria can fix nitrogen using enzymes containing iron and molybdenum. Lightning also fixes nitrogen by forcing nitrogen and oxygen to react in the high-energy conditions of electrical discharge. Life on other planets would need some source of biologically available nitrogen, either through similar fixation processes or through nitrogen already present in reactive forms. Phosphorus plays a unique and critical role in biochemistry. It's part of the backbone of DNA and RNA, linking the sugar molecules together into the long chains that store genetic information. It's also central to ATP, the molecule that stores and transfers energy in cells. Phosphate groups can be added to and removed from molecules to regulate their activity, serving as switches that turn cellular processes on and off. There is no obvious substitute for phosphorus in these roles. Unlike carbon, nitrogen, and oxygen, which are abundant in the universe, phosphorus is relatively rare, created only in certain types of stellar processes. A planet poor in phosphorus might struggle to develop complex life, at least of the kind we would recognize. Sulfur contributes to protein structure through disulfide bonds, connections between sulfur atoms in different parts of a protein that help the protein fold into its proper three-dimensional shape. Some organisms use sulfur compounds in their metabolism instead of or in addition to oxygen. Near hydrothermal vents on Earth's ocean floor, bacteria oxidize hydrogen sulfide, the compound that smells like rotten eggs, to generate energy. Entire ecosystems build on these chemosynthetic bacteria, demonstrating that sunlight and photosynthesis are not necessary for life. An alien world with extensive volcanic or hydrothermal activity could support life based on sulfur chemistry, even in complete darkness. Trace elements, though needed in tiny amounts, are essential for many biological processes. Iron is central to hemoglobin, the protein that carries oxygen in blood, and to many enzymes involved in energy metabolism. Magnesium sits at the center of chlorophyll molecules, enabling photosynthesis. Zinc, copper, manganese, and other metals serve as cofactors for enzymes, helping catalyze reactions that would otherwise proceed too slowly to sustain life. An alien biochemistry would likely require its own set of trace elements, perhaps using metals common on its world but rare on Earth, or finding entirely different solutions to catalysis and molecular structure. Water serves as the solvent for biochemistry on Earth, the medium in which all cellular chemistry occurs. Water has remarkable properties that make it ideal for life. It remains liquid across a wide temperature range, from 0 to 100 degrees Celsius at Earth's atmospheric pressure. It has a high heat capacity, meaning it resists temperature changes, which helps organisms maintain stable internal temperatures. Water molecules are polar, with a slight positive charge on one end and a slight negative charge on the other, allowing water to dissolve ionic compounds and interact with many different types of molecules. The hydrogen bonds between water molecules create surface tension, capillary action, and the unusual property that ice floats on liquid water, a characteristic that has profound implications for life in oceans and lakes. But is water necessary for life, or might other liquids serve as solvents for alternative biochemistries? Ammonia has been proposed as a possible alternative. Ammonia remains liquid at much colder temperatures than water. It freezes at -78 degrees Celsius and boils at -33 degrees Celsius at Earth's atmospheric pressure. A very cold planet, too cold for liquid water, might have lakes or oceans of liquid ammonia. Ammonia shares some of water's properties. It's polar, can form hydrogen bonds, and dissolves many substances. However, ammonia is a less effective solvent than water for many compounds, and the biochemistry that could operate in liquid ammonia would necessarily be very different from Earth's water-based life. Methane and ethane, though non-polar and very different from water, exist as liquids on Titan, Saturn's largest moon. Titan has lakes and rivers of liquid hydrocarbons on its surface, creating a hydrological cycle remarkably similar to Earth's water cycle, but operating at temperatures around -180 degrees Celsius. Could life exist in these hydrocarbon lakes? The chemistry would be completely unlike anything on Earth. Reactions that occur readily in water might not occur at all in methane, while entirely different reactions become possible. Cell membranes would need to be built from different molecules. The lipid membranes used by Earth cells wouldn't function in liquid methane. Energy metabolism would follow different pathways. But some scientists argue that the sheer strangeness of Titan's environment doesn't preclude life, only life that operates on unfamiliar principles. Supercritical fluids represent another possibility. Under high pressure and high temperature, substances enter a supercritical state where the distinction between liquid and gas breaks down. Supercritical carbon dioxide, for instance, behaves as both liquid and gas simultaneously, with properties of each. Deep beneath the surfaces of certain planets, conditions might create supercritical water or other supercritical fluids that could potentially serve as solvents for exotic biochemistries operating under extreme conditions. Energy sources drive all biochemistry. On Earth, sunlight powers most ecosystems through photosynthesis. Plants and photosynthetic bacteria capture light energy and use it to build organic molecules from carbon dioxide and water. These organic molecules then flow through food chains, ultimately providing energy for all other organisms. But many alternative energy sources exist. Chemical energy from redox reactions, where electrons transfer from one molecule to another, can sustain life in complete darkness. Radioactive decay in a planet's interior could provide steady energy through the heat it generates, potentially supporting life in subsurface environments for billions of years, even if the star above has long since died. The origin of life, the transition from complex chemistry to living organisms, requires conditions where organic molecules can form, concentrate, and begin the process of self-replication and evolution. On Earth, this might have occurred in tidal pools, in hydrothermal vents, in ice, or even in the atmosphere. The exact location and mechanism remain uncertain, but the chemistry required involves forming increasingly complex molecules from simpler precursors, eventually creating molecules capable of catalyzing reactions, including their own replication. This requires an energy source to drive uphill reactions that create complexity from simplicity, fighting against entropy. It requires some form of containment, membranes or surfaces, to concentrate molecules and create distinct chemical environments. And it requires time for random chemical processes to explore countless possibilities until self-replicating systems emerge. The universality of certain chemical principles suggests that life elsewhere, no matter how alien, would still obey the same rules of chemistry and thermodynamics that govern Earth's life. All life must extract energy from its environment and use that energy to create and maintain complex organization. All life must reproduce, passing information to offspring. All life must evolve through variation and selection. These requirements constrain the chemistry of life, regardless of what specific molecules are involved. Carbon is not the only possible basis for complex chemistry, water is not the only possible solvent, and oxygen is not the only possible energy source, but any living system must solve the same fundamental chemical problems: how to capture and store energy, how to build complex molecules, how to replicate information, and how to maintain organization in a universe that constantly tends toward disorder. The chemistry required for life beyond Earth encompasses the familiar carbon, water, proteins, and DNA, and the exotic silicon biochemistry in hydrocarbon seas, life in supercritical fluids, using metals we've never heard of, organisms metabolizing on reactions we've never imagined. The universe provides the raw materials everywhere: hydrogen from the Big Bang, heavier elements forged in stars and scattered through supernova explosions. Every planet, moon, and asteroid contains chemistry, happening constantly through radiation, temperature gradients, and the simple mixing of different compounds. Whether that chemistry crosses the threshold into life depends on having the right combination of elements, solvents, energy sources, and time, ingredients that might exist on countless worlds throughout the cosmos, waiting for chemistry to become biology in endless variations on the theme of life. How we measure the weight of space objects. When astronomers announce that Jupiter has more than 300 times Earth's mass, or that a distant black hole contains several billion times the Sun's mass, these numbers might seem impossibly precise. How can we possibly weigh objects millions or billions of miles away, objects we can never visit or touch, objects that are sometimes completely invisible? The answer lies not in direct measurement, but in observing how these objects interact gravitationally with their surroundings. Mass reveals itself through gravity, and by watching how objects move under gravitational influence, astronomers can calculate masses with remarkable accuracy using principles that Isaac Newton worked out more than 300 years ago. The fundamental principle is simple. The more massive an object is, the stronger its gravitational pull, and the faster other objects must move to orbit it. This relationship, encoded in Newton's law of universal gravitation and his laws of motion, allows us to determine mass from orbital motion. If you know how fast something orbits and how far away it is from the object it's orbiting, you can calculate the central object's mass. For planets in our solar system, we measure their masses by observing their moons. Jupiter has dozens of moons, and each one's orbital period and distance from Jupiter reveals Jupiter's mass. The formula is straightforward in principle. The orbital period squared is proportional to the orbital distance cubed divided by the central mass. By measuring the period and distance, we can solve for the mass. The more massive the central object, the faster moons must orbit at a given distance to avoid falling inward. Jupiter's moon Io orbits very close to Jupiter and completes an orbit in only about 42 hours. Because Jupiter's immense mass creates powerful gravity, our moon takes 27 days to orbit Earth at a similar distance because Earth is much less massive than Jupiter. For planets without moons, Mercury and Venus, determining mass required more ingenuity. Before the space age, astronomers studied how these planets affected each other's orbits through their gravitational interactions. When two planets pass relatively close to each other, their gravitational pulls slightly deflect each other's paths. By precisely measuring these tiny perturbations over years of observations, astronomers could infer the masses of the planets involved. Space probes visiting these planets provided much more accurate mass measurements by observing how the planet's gravity affected the spacecraft trajectories. Measuring Earth's mass required understanding gravity itself. In the late 18th century, British scientist Henry Cavendish performed a delicate experiment using a torsion balance, a horizontal bar suspended by a thin wire with lead spheres at each end. By bringing large lead masses near the suspended spheres and measuring like the tiny twist in the wire caused by gravitational attraction, Cavendish determined the strength of gravity between known masses. This measurement, combined with the known acceleration of gravity at Earth's surface, allowed calculation of Earth's mass. The experiment is sometimes described as weighing the Earth, though it really measured how strongly Earth's gravity pulls compared to the gravity between laboratory masses. For the Sun, measuring mass is straightforward because Earth and all other planets orbit it. Earth orbits the Sun at a distance of about 150 million kilometers with an orbital period of 1 year. Plugging these numbers into the orbital equation gives the Sun's mass about 2 times 10 to the 30th power kilograms, or about 330,000 times Earth's mass. The exact same calculation works for any star with planets. Measure the planet's orbital distance and period, and you can determine the star's mass. Binary star systems, two stars orbiting each other, provide mass measurements for individual stars. By watching the stars orbit their common center of mass and measuring their orbital periods, distances, and velocities, astronomers can determine both stars' masses separately. This technique has measured thousands of stellar masses, revealing the relationship between a star's mass and its other properties, like luminosity and temperature. These measurements show that stars range from about 8% of the Sun's mass for the smallest red dwarfs up to perhaps 150 times the Sun's mass for the most massive stars. For more distant objects, techniques become more sophisticated but still rely on gravitational effects. Galaxies contain hundreds of billions of stars, and measuring a galaxy's mass means measuring how fast stars and gas orbit within it. By observing the rotation speeds at different distances from the galactic center and applying the same orbital principles, astronomers can calculate the total mass enclosed within each radius. This technique revealed the existence of dark matter. The rotation speeds in the outer parts of galaxies are far too high to be explained by the visible stars and gas alone, requiring the presence of large amounts of invisible mass. Galaxy clusters, groups of hundreds or thousands of galaxies, have their masses measured through multiple techniques. One method observes the motions of individual galaxies within the cluster. The galaxies orbit within the cluster's gravitational potential, and their velocities reveal the cluster's total mass. Another technique uses gravitational lensing, the bending of light from more distant galaxies by the cluster's gravity. The amount of bending depends on the cluster's mass, so by measuring how background galaxies appear distorted, astronomers can map the cluster's mass distribution, including dark matter. Black holes present special challenges because they are invisible and often have no nearby objects in simple orbits. For stellar mass black holes in binary systems, astronomers measure the orbital motion of the visible companion star. The star's velocity and orbital period reveal the black hole's mass, even though the black hole itself emits no light. This technique confirmed that several X-ray binary systems contain objects too massive to be neutron stars. They must be black holes. Supermassive black holes at galaxy centers are weighed by observing stars or gas orbiting near them. The Milky Way's central black hole, Sagittarius A star, has its mass measured precisely by tracking individual stars as they orbit. One star, designated S2, completes an orbit every 16 years in an elongated ellipse that brings it within about 120 times Earth's distance from the Sun, extremely close by galactic standards. By measuring S2's position and velocity throughout its orbit, astronomers calculated the black hole's mass at about 4 million times the Sun's mass. This measurement is accurate to within a few percent, despite the black hole being 26,000 light-years away. More distant supermassive black holes are measured through the motion of stars or gas closer to the black hole than telescopes can individually resolve. Instead, spectroscopy measures the range of velocities present in the light coming from the galaxy's central region. Broader velocity distributions indicate faster-moving material, which requires more mass to keep the material bound. Using this technique, astronomers have measured black hole masses ranging from millions to billions of solar masses in galaxies across the universe. Gravitational waves from merging black holes provide another mass measurement technique. When two black holes spiral together and merge, they emit gravitational waves, ripples in space-time itself, detected by observatories like LIGO. The frequency and amplitude of these waves encode information about the black hole's masses. The first gravitational wave detection in 2015 came from two black holes weighing about 29 and 36 solar masses that merged into a single black hole of about 62 solar masses. with 3 solar masses worth of energy radiated away as gravitational waves during the collision. For objects we can visit with spacecraft, mass measurements become more direct. The spacecraft's trajectory bends as it passes the object, with the deflection determined by the object's mass. By tracking the spacecraft's position using radio signals and measuring the Doppler shift in those signals, mission controllers determine the trajectory precisely. Comparing the observed trajectory to computer models reveals the mass that must have caused that particular deflection. This technique has measured masses of asteroids, comets, and moons with no satellites of their own. Small asteroids present particular challenges. Without satellites, and too small to significantly affect spacecraft at typical flyby distances, their masses remained uncertain until spacecraft flew very close or even orbited them. The near-Shoemaker spacecraft orbited asteroid Eros for a year, precisely measuring Eros's mass and density. The Hayabusa and OSIRIS-REx missions orbited small asteroids, Ryugu and Bennu respectively, measuring their masses through orbital mechanics and revealing that both asteroids are loose rubble piles rather than solid rocks. The precision of mass measurements varies enormously. The Sun's mass is known to about 7 significant figures. Earth's mass is known even more precisely because we can measure Earth's gravitational field from satellites in low orbit. Jupiter's mass is known very precisely from spacecraft tracking, but the mass of a distant galaxy might be uncertain by 10 or 20%, and masses of galaxy clusters can be uncertain by even more, particularly if dark matter doesn't follow the same distribution as visible matter. Understanding the limitations matters. When astronomers quote a mass, there's always uncertainty attached. Reporting that a black hole contains about 4 million solar masses acknowledges this uncertainty. The actual value might be 3.8 million or 4.2 million, and that range represents our measurement precision, not variability in the black hole's mass. All these techniques ultimately trace back to gravity, the fundamental force that governs how massive objects interact across space. Mass creates gravity, gravity creates motion, and by observing that motion precisely, we can work backward to determine the mass that caused it. From moons orbiting planets, to galaxies orbiting within clusters, from binary stars wheeling around each other, to stars orbiting supermassive black holes, the cosmos is filled with objects whose motions reveal the masses of the bodies that control them. By watching these cosmic dances and applying the mathematical laws that Newton first articulated, astronomers can weigh objects from the smallest asteroids to the largest galaxy clusters, measuring masses across a range spanning more than 20 orders of magnitude. From asteroids weighing billions of tons to galaxy clusters weighing millions of trillions of times more than the Sun, all without ever placing these objects on a scale, relying instead on the universal language of gravity that connects everything in the cosmos through the elegant mathematics of orbital motion.